So in this video, we're going to be talking about the ideal gas law. So this is chapter 10, talking about gases. This is going to be extremely important whenever you're looking at any sort of problem in chapter 10. So the ideal gas law, or the ideal gas equation, states that PV is equal to nRT. And if you don't take anything from chapter 10 or general chemistry, I hope that this is one of the equations that you'll take along with you. This is extremely important, and it tells us that pressure times volume is equal to the moles times the ideal gas constant times your temperature. And there's a few things that you need to note. Your pressure and your volume can be in different units. Whatever units you have for your pressure and volume, you need to make sure that your ideal gas constant follows those. So if you're using liters in atmosphere, your ideal gas constant is going to be that 0.08206. If you're using meters cubed in pascals, you're going to use the 8.314. And if you do liters times torr, you're going to use the 62.36. There's a few, I think there's one more R. And again, if you don't have both of those, you're going to need to make sure that you're doing some converting. So if you need to convert pascals to atmospheres or meters cubed to liters, because one of those units is not matching, just keep that in mind. Another thing to keep in mind, your temperature is always going to be in Kelvin. So that's something that could definitely trip you up. If it gives it to you in Celsius or Fahrenheit, that's something that doesn't budge. Your temperature will always be in Kelvin. And if you look at your ideal gas constant, you can see that it's always divided by moles times Kelvin. So some important implications of this ideal gas law, or this ideal gas equation, tells us that pressure and volume are inversely proportional. So if my moles don't change, and if my temperature doesn't change, if I decrease volume, my pressure is going to increase, and if I increase volume, my pressure will decrease. So making sure that everything is constant, then those would be inversely proportional. So let's say you were going to be expanding a balloon. So if you were to expand or heat up a balloon with a certain amount of gas in it, then our next step would show that volume and temperature are directly proportional. So again, if I heat up that balloon, my temperature is going to be increasing, which means my volume is going to be increasing, and vice versa. I don't know if in high school or in college, or if you've gotten any demonstrations in your labs, whenever you stick a balloon in liquid nitrogen, you're decreasing that temperature, and you pull out the balloon and your balloon's all shriveled up. Well, that's because your volume has also decreased, and they're directly proportional. And last but not least, this tells us that our moles and our volumes are directly proportional. So again, if you're blowing up a balloon, the more moles of air you put in, the greater and greater that balloon is going to expand. So your volume and your moles are going to be directly proportional. So individual gas laws. There's a bunch of different individual gas laws, but really in any math problem, you can make these different relationships by using PV is equal to nRT. So Boyle's law tells us that the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. So that means that your P1V1 is equal to your P2V2. So again, if nothing changes, your moles, your temperature, whatever you do to that pressure, your volume is going to have to be inversely proportional. Your Charles law tells us the volume of a fixed amount of gas at constant pressure is directly proportional to the absolute temperature. So again, that volume and temperature. So a lot of these are very self-explanatory. You can go through and look at the individual gas laws. But really, if you want to compare all of these things, use PV equal nRT, and then you can ratio them out. So at the bottom, this says P1V1 over N1T1 is equal to P2V2 over N2T2. Y'all could have found this if y'all did this ratio using P1V1 equals N1R1 T1, and your R's are the same. So you can, again, get these different ratios. And if you forget all these individual gas laws and you're doing a math problem, go to that PV equals nRT. It will help you a lot, and you can probably try and work your way through the problem. So let's do a practice problem. So this says that a gas sample occurs at a volume of 16.4 liters I'm going to jot that down, at 27 degrees Celsius and 0.300 atmosphere. So something important that we're going to need to know is what R value are we going to use. So our units are liters and atmospheres, so I'm going to hop back really quick to show you that here is our box for our R values. We said that we had liters and atmospheres, so the R value we're going to use is at 0.08206. So that is liter atmosphere per mole Kelvin. Another important thing that our R value can tell us is that we need to, again, change our temperature to Kelvin because we're always going to be working with that in Kelvin. So to do that, our temperature is equal to 27 degrees Celsius. To change to Kelvin, I'm going to add 273.15. And I'm going to get 300.15 Kelvin. So now that we have our temperature and our R value, we're going to just start plugging in with our PV equal to nRT. It asks us how many moles of gas are present. So what I'm going to do is I'm going to solve for my number of moles by dividing by RT. So I'm going to get N is equal to PV over RT. If you wanted to plug in numbers before you solve for N, that's perfectly fine. I like to solve for the thing I'm looking for first so that all I have to do is plug them into one equation and not have to move over numbers. So now I have my pressure, which we said was 0.300 atmosphere, times my volume, which was 16.4 liters, over our R value, which we said we were going to use was 0.08206 liters atmosphere per mole K, times our temperature in Kelvin, which is 300.15 Kelvin. So let's look at our units. So I have atmospheres cancel atmospheres, liters cancel liters, and Kelvin cancel Kelvin. So now I'm just left with 1 divided by 1 over moles. So if we were going to do algebra, keep, change, flip, so I'd have moles as my final unit. So my units are checking out. And now I'm just going to plug this into the calculator. And I'm going to get 0.1998 moles. So again, using sig fig rules, I need 3 significant figures in the end. So I use this PV equal nRT to solve for one of the units. And I would encourage that you go through, practice different types of applications for PV equals nRT. There's a lot of different ways you can relate certain things. Maybe you had something that was at a certain pressure and I released that pressure and you want to find out the volume now. So you can always go online to look at the back of the book, ask the professors, and I know that there's some homework problems too that you can work through on this stuff. So let's go to a different practice problem. Okay, awesome. So this practice problem says how many liters of NH3 gas at 850 degrees Celsius and 5 atmosphere are required to react with 1 mole of O2 gas in this reaction. So again, kind of look at this as dimensional analysis. So we can't directly go from moles of O2 to liters of NH3. but what we can do is compare moles to moles. So using this reaction, I know that for every 5 moles of O2, I need 4 moles of NH3 to react. So this is helping us find our moles of NH3. So I'm going to get 0.800 moles of NH3. I need to fully react with 1 mole of O2. So now I have moles, and now I can look for how many liters that would be. So using our ideal gas equation, PV is equal to nRT. I'm trying to find liters, so I'm trying to find volume. So I'd get nRT over P, which is our pressure. Our R value is going to be needed to be in the units of liters in atmosphere. So we're going to use the exact same R value we did in the previous slide. So we're going to use 0.08206 liters atmosphere per mole K. The more you work through these problems, the more you're going to become familiar with this unit and the 8.314, just because you'll be using so much repetition and going through them. So don't worry if you don't know them now. Maybe jot them down on a note card. The more you practice, the more you're going to become familiar with, oh, I need to use this R value. So that will be our R value. Our pressure was 5 atmosphere. Our volume we're looking for, and our temperature was 850 degrees Celsius, but we need that temperature to be in Kelvin. So what I'm going to do is add 273.15 to get us 1103.15 Kelvin. So now that I have Kelvin, our temperature in Kelvin and not in degrees Celsius, we can start plugging in. So our volume is equal to our moles, which we said was 0.800 moles, times our R value, which is 0.08206 liters atmosphere per mole K. And then our temperature was 1103.15 K. And we're all going to divide that by our pressure, which is 5.00 atmosphere. So now that we have that, we're going to just plug all of that into the calculator. Again, remember your significant figure rules. In this case, we're going to have 3 significant figures. So our final answer is 14.4839 liters. So we're going to get 14.5 liters needed. So again, this can kind of incorporate the stoichiometry that you know and the reactions that you know. And now we're going to add this onto our mole map. So we can go from moles to liters by using this ideal gas law. So in this case, we're talking about the gas liters. Again, you could go from moles to liters using molarity from the aqueous chemistry chapter. So again, keep adding on to that mole map. It's super important. You're going to find a lot of different ways to convert, I call it fancy dimensional analysis. It again is just comparing these different dimensions and using this equation that we know to convert from moles to liters and things like that.